Assalamu alaikum wa rahmatullah. Bismillah ar-Rahman ar-Rahim. Dear students, I'm trying to create like a set of offline videos to help you with the study. So the first video is going to be about some exercises for chapter 3, data and signals. So we'll warm up with this exercise. So what is the bandwidth of a signal that can be decomposed into 5 sine waves with frequencies 0, 20, 50, 100, and 200 hertz. All peak amplitudes are the same. So this is simply for the frequency domain. So we have an amplitude at frequency 0, which has a specific value that's not mentioned, and then we have at 20, which is the same, and we have at 50. And then we have 100, and we have 200. All right, so simply the bandwidth, as we all know, is the maximum frequency minus the minimum frequency, which is 200 minus 0, that's 200 hertz. So that's a warm-up exercise. So the next one is regarding a periodic composite signal with a bandwidth of 2000. So now we have the bandwidth, which is composed of 2 sine waves. All right, so we have a composite periodic signal with a specific bandwidth, 2000. The first frequency is at 100. With a maximum amplitude of 20 volt. If we have a bandwidth of 2000, so what is the maximum frequency here? It's 2100 hertz, because the total bandwidth is 2000, and the amplitude of this one is actually 5 volt. So this is how we draw the this is the amplitude, of course. So this is how we draw the bandwidth or the frequency spectrum of this signal. All right, so third exercise is talking about bit rate, how to calculate the bit rate. So if we have a signal in which one bit rate lasts 0.001 seconds, so basically the bit rate equals to 1 bit divided by 0.001 second, that's 1000 bits per second. All right, so if a signal in which one bit lasts 2 milliseconds, so n equals 1 bit will last 2 times 10 to the power minus 3, that's 500 bits per second. All right, so if a signal has 10 bits last 20 microseconds. So here n equals 10 divided by 20 times 10 to the power minus 6. So that's 0.5 times 10 to the power 6. So that's 500 kilobits per second. Okay, don't forget the units. Always have to include the units. All right, so next exercise talks about a device is sending out a data at a rate, so now we have the rate 1000 bits per second. So how long does it take to send out 10 bits? Well, the best approach to go about this exercise is to use the X rule. So if we have what is the meaning of the rate? The meaning of the rate is that we have each 1000 bits take 1 second. So each 1000 bits take 1 second. So what is the time to take that 10 bits will take? So we need to find that time. So this time is actually based on the X rule. So this time is, so the time equals 10 bits times 1 second divided by 1000 bits. So that's 0.01 second. Okay. So the next one, how long does it take to send out a single character of 8 bits? Again, if we have 1000 bits take 1 second, so how long does it take to send 8 bits? So the time equals 8 divided by 1000, that's seconds to send one character. All right, so how long does it take to send a file of 100,000 characters? Each character in that case is 8 bits. All right, so time. So if we have 1000, take 1 second. So 100,000 times 8 take how long? Okay, so the time equals 100,000 times 8 divided by 1000. That's 800 seconds. So next exercise. So what is the bit rate for the signal in the figure? Okay, so this bit rate has how many bits? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bits take 16 nanoseconds. So what is the bit rate? So bit rate equals, so we have 8 bits divided by 16 times 10 to the power minus 9. Nanosecond is minus 9. So that's 0.5 times 10 to the power 9. So that's 0.5 gigabits per second. Okay. Okay. Next. So what is the bandwidth of a composite signal shown in the figure? So this bandwidth is, so what do we know about this signal? So this signal is a periodic signal because it's represented by discrete frequency components, and between each two frequency we have 5 hertz. So bandwidth is 5 plus 5 plus 5 plus 5 plus 5, or 5 times 5, that's 25 hertz. Okay, very easy. Okay, so next. Now, a non-periodic composite signal. We know that a non-periodic composite signal can be represented in the frequency domain using continuous signal or analog signal. So this non-periodic composite signal contains frequencies from 10 to 30 kilohertz. So that's, if this is the frequency, so it starts from 10 kilohertz to 30 kilohertz. Okay, so the peak amplitude is 10 volt for the lowest and the highest. So here we have 10 volt, and here we have 10 volt. And for the 20 kilohertz, which is in the middle, the amplitude is 30. So here it's 30 volt. So assuming that the amplitudes change gradually from minimum to maximum. So here again, similar to the exercise that we have done in class, I didn't tell you whether this gradual relationship is linear or non-linear or whatever. So if you do it this way, it's fine. So this is a continuous signal. So if I change this word to periodic, then remember that this has to be a discrete signal. So for this case, it's a continuous signal because it's non-periodic. Okay, so this exercise here talks about a TV channel that has a bandwidth of 6 megahertz. If we want to send a digital signal using one channel, what are the data rates? Remember the equation that we have discussed in class. So the bandwidth for the case of one harmonic is actually n over 2. So this is for one harmonic. Okay. So for the case of two harmonics, we said that the bandwidth is equal to 3n over 2. This is for two harmonics. And for three harmonics, we said that the bandwidth equals 5n over 2. This is for three harmonics. Right? So this leads to the fact that if we have the bandwidth already, this bandwidth is 6 megahertz. So for this case, 6 times 10 to the power 6 equals n over 2. So n in that case is 12 megabits per second. So n is 12 megabits per second. So for this case, if 6 times 10 to the power 6 equals 3n over 2, so n in that case is 4 megabits per second. And for this case, it's 6 times 10 to the power 6 equals 5n over 2. So in that case, it's n equals 12 divided by 5 megabits per second. Okay, so that's the solution for the three cases if we have one harmonic, two harmonics, or three harmonics. So next exercise, if a signal travels from point A to point B. So at point A, so this is point A, the signal power is 100 watt. At point B, the signal power is 90 watt. So what is the attenuation in decibel? Of course, obviously it's an attenuation because the signal has decayed. So this is point B. So the attenuation, since the requirement is in decibel, so we know that the attenuation is 10 log 10 of P2 divided by P1. Okay, so that's 90 divided by 100. So this is 10 log 10 of 0.9. Next, so if the attenuation of a signal is minus 10 decibel, what is the final power if the original signal was 5 watt? So we know that this attenuation, so attenuation equals 10 log 10 of P2 divided by P1. Okay, so minus 10 equals 10 log P2 divided by 5. So we need P2. So easily, so P2 equals 10 to the power minus 1 divided times 5. So that's 0.5. Okay, so 0.5 watts. Do not ever forget the unit. All right, so next, a line has a signal to noise ratio of 1000. So SNR equals 1000, and it's unitless. Pay attention to that. Unitless, it's not decibel, which means that this is actually the ratio of the signal power divided by the noise power, and the bandwidth is 4000 kilohertz. Okay, what is the maximum data rate? So we know that the maximum bit rate C, or the capacity, equals bandwidth log 2 of 1 plus SNR. So that's 4,000 times 10 to the power 3 log 2 of 1 plus 1,000. So this will be around 40,000 bits per second. And you can do it using a calculator. Okay, so next. If the peak voltage value of a signal is 20 times the peak voltage value of a noise. All right, so remember that what is the signal to noise ratio? Remember, the signal to noise ratio is the signal power divided by the noise power. This is the signal to, not the decibel. This is the actual signal to noise ratio. Okay, so remember that this is the amplitude, not the power. So if the signal amplitude is 20 times, so what is the ratio between the signal power and the noise power? Well, signal power is proportional to the signal amplitude square. Similarly, noise power proportional to noise amplitude square. So which means that this ratio is actually the signal amplitude divided by the noise amplitude square. Okay, so this ratio is 20 times. So then signal to noise ratio equals 20 square, which is 400. And of course, signal to noise ratio in decibel equals 10 log 10 of 400. Okay, so remember that the signal power is actually proportional to the square of the signal amplitude. It's next. So what is the theoretical capacity of a channel in which the following cases? So we have a channel of a bandwidth 20 kilohertz and the SNR in decibel is 40. Well, we know that again the capacity equals bandwidth log 2 of 1 plus SNR, or if the SNR is high, in so this is the bandwidth times SNR divided by SNR in decibel divided by 3. Okay, so this case is obvious, this case is obvious, this case is a little bit borderline. So we can, so for A we can easily say that the capacity equals 20 times 10 to the power 3 times 40 divided by 3. So this is around 266 kilobits per second. For the case B, C is equal. So for the case B, SNR in decibel equals 4. So this means that 10 log 10 of SNR equals 4. So this means that the actual SNR equals 10 to the power 0.4, which is 2.5. Okay, so the capacity equals 20 times 10 to the power 3 log 2 of 1 plus 2.5. So that's for the case C. Assume that 20 is too high, so we can calculate capacity equals again 20 times 10 to the power 3 times 20 divided by 3. So that's 400 divided by 3 kilobits per second. So it's around 133 kilobits per second. Next, if we need to send a minimum bit rate of 128 kilobits per second over a noiseless channel with a bandwidth of 20 kilohertz, how many signal levels do we need? Well, this refers to, of course, the Nyquist theorem, and we know that using Nyquist theorem, the bit rate can be represented by 2 times the bandwidth times log 2 of the number of levels. Okay, so if we have 128 times 10 to the power 3 equals 2 times 20 times 10 to the power 3 log 2 of L. So the log 2 of L equals 128 divided by 40, that's around 3.2. So remember that 3.2 here is the number of bits that can be represented using one level, and since this is the number of bits, it has to be integer. So we cannot use number of bits equal 3.2. So we have to make it 4. So we have to do that. We have to make this 4. So the number of levels equals to 2 to the power 4. That's 16 levels. So in other words, we need at least 16 levels to represent this bit rate or more. So of course, this 16 bit will give you 4. So then the actual bit rate that you will get, it will be 4. It will be 4 here times 40. So 4 times 40, that's 160. So L will give you a bit rate of 160 kilobits per second, which is of course more than 128, because if we use 3 bits, it will be less than 128. So we have to use 4 bits, or in other words 16 levels. Okay, so how many bits can fit on a line with a 2 millisecond delay represented on a line with a 2 millisecond delay if the bandwidth of the link is 1 megabits per second? So this of course refers to the bandwidth delay product, or the bandwidth times the delay. So as we said, as we discussed in class, bandwidth delay product refers to the number of bits that we can fit on the transmission line at any point in time. So for this case, we have the bandwidth delay product equals 1 times 10 to the power 6 times 2 times 10 to the power minus 3. So that's 2000 bits. And of course, if we multiply the bandwidth by 10, this leads to 20,000 bits. If we multiply it by 100, so that's 200,000 bits. So this is the bandwidth delay product, or the number of bits that can fit on the transmission line. So this is the last exercise. So what is the total delay for a frame of size 5 million bits? So the frame size is 5 million bits that is being sent on a link with 10 routers, each having a queuing delay or a queuing time of 2 microsecond and a processing time of 1 microsecond. So that these 2 microseconds and 1 microsecond happens at every router. The length of the link is 2000 kilometers and the speed of light inside the link is 2 times 10 to the power 8, and the link has a bandwidth of 5 megabits per second. What is the component of the delay, of the total delay that it's dominant, and which one is actually negligible? So we know that the total delay equals to transmission delay plus propagation delay plus queuing plus processing delay. Remember, these two they happen at every router, so we have to multiply them by 10. All right, so transmission delay, so we know that transmission delay is simply the length of the frame divided by the bandwidth, which is, the length is 5 times 10 to the power 6, and the bandwidth is 5 megabits per second. That's also 5 times 10 to the power 6, so that's 1 second. All right, propagation delay equals the length of the link divided by the speed. Okay, so the length is 2000 times 10, because it's kilometers, 2 times 10 to the power 3 divided by 2 times 10 to the power 8. So that's 0.01 seconds. Okay. All right. So now the queuing delay is 1 microsecond, so 1 times 10 to the power minus 6 times 10 routers, and processing delay equals also the queuing, sorry, is 2 microsecond, and the processing time is 1 microsecond, so 1 times 10 to the power 6 minus 6 times 10 routers. So this one is 20 microsecond, and this one is 10 microsecond. And of course the total delay is the summation of all these 4 components. So you have 1 second, 0.01 second, and you have 20 microsecond and 10 microsecond. Of course, the dominant one is the transmission delay, and the negligible one is the queuing delay and the processing delay, which is what we have discussed in class. Really, the processing delay at the router is usually the least component in terms of value, and it's usually neglected. So the dominant component here is the transmission delay. So thank you very much, and this ends this set of slides for exercises regarding chapter 3.